Okay, so we're going to take a look at atomic theory and the atom. I'm going to go through the atom and how historically we discovered it, and all the postulates and kind of all of the stuff coming together. And I'm going to record another video on kind of the important things to know about the atom. So this first video, the very beginning of 3.3, this is important, but not like super important. This might help you understand it, but at the end of the day, the stuff in the next video is really the kind of the meat of what chemistry is. This is kind of the very cool, like, wow, I can't believe they discovered that moment. But so that's what we're going to take a look at. So Dalton was the first. He's kind of known as the grandfather of chemistry. Okay, so Dalton developed these atomic theories about 230 years ago or something like that, right in the beginning, right at the beginning of chemistry. So he's kind of the grandfather. So these things have, again, you have to recognize that he came up with these postulates, these Dalton's postulates. He came up with these before anyone could see anything smaller than, through a microscope. Okay, so it's really impressive that he was able to do this in the way by which they discovered this. So first and foremost, matter is composed of atoms. Okay, so matter is composed of atoms. Simply saying that the atoms are the smallest unit of an element. Every single atom has every single atom, the smallest thing you can get is an atom, right? A carbon atom, a hydrogen atom, a lead atom, all of those things, that's the smallest particle. And you use that like Legos to build something, okay, to make compounds, to make matter. Okay, so matter is composed of atoms as the principal unit. As a quick aside, we know that that's not correct anymore. I mean, it is. But now we know about electrons, protons, neutrons. We know about quarks, which are with what make up protons, neutrons, and electrons, so on and so forth. But again, 230 years ago, pretty impressive that you can come up with that. So for all intents and purposes, we don't really need to worry about that right now. Matter is composed of individual atoms as the smallest kind of building blocks. Two, he said that elements, okay, so atoms of one specific type, one type of atom, which is an element, which is one type of atom, has a mass that is characteristic of the element and is the same for all atoms of that element. And basically, what he is saying, and they have identical chemical properties. So, what he is saying here is if I have a carbon atom, every single carbon atom is going to be the exact weight and react the same chemically, right? So, I don't have different types of chemical reactions with different types of carbons. We just simply have elements behave and all act the same. And that's really, they have the identical behaviors or they behave the same. Okay, again, we know that isotopes exist. We have different types of carbon, but for the most part, they have the identical chemical properties. Okay. Atoms of one element differ in properties from atoms of other elements. Gold is different than silver, which is different than hydrogen. So elements are different than one another. Okay. So that is, again, impressive that he comes up with all of this. Next one, now we're getting into compounds. Compounds consist of atoms of two or more elements. We know that in a small whole number ratio. Uh, Compounds consist of atoms in two or more elements in a small whole number ratio. H2O, we know, consists of two hydrogens, one oxygen. Copper oxide, one copper, one oxygen. Okay, so we always have a compound is always, basically what this is saying is water is always two hydrogen and one oxygen. Okay, so there's no changing that. Water is always the same thing. Doesn't matter where you go or what water you have, it's always going to be the same compound. And then finally, we know this as well, atoms are neither created nor destroyed, but they're rearranged. Okay, so if I have a reaction, okay, so if we have something like burning of hydrogen, hydrogen combines together with oxygen to give me water. What you simply have is, I'm going to put twos in front of here. Here I have 2 hydrogens reacting with 1 oxygen. I guess I should do it this way. Too small. Make the oxygens a little bigger. 2 oxygens to give me, to give me 2 water molecules. So here's my oxygen, and I have 1, 2 hydrogens, 1, 2 hydrogens. You get the gist. What you notice on the left is I have a total of 4 hydrogens. On the right, I have 4 hydrogens, 2 oxygens, 2 oxygens. Okay, so we're always going to have the same stuff on the left as we do on the right. So before the reaction and after, we're always going to have the same amount of stuff. Okay, so again, Dalton's postulate's pretty neat that he could come up with that. Matter is made up of atoms. Elements are composed of different combinations of specific sets of atoms. Elements always behave the same. Elements are behaving differently than one another, and we're never going to lose an atom. They always kind of just rearrange themselves into something else. Okay, and that's the important part of that. Okay, so over time, this worked for us. We were able to do a bunch of chemistry and descriptive chemistry and kind of look at compounds and all of that stuff. And then we discovered that there are subatomic particles. Remember, I said that there are subatomic particles. There absolutely are. So what we really have is, and this is a bad representation of the atom on the left, what we really have is we have a nucleus in the middle and electrons around the outside. Okay, and what they discovered is J.J. Thomson in 1897 discovered using the cathode ray tube that electrons are a thing. I can fire electrons. I can essentially have electrons and I can bend them based on putting a magnet near this beam. So if you put a negative magnet, the beam will bend away from this because it repels electrons. Turns out electrons are negative. So he discovered the electron with the cathode ray tube experiment. By the way, cathode ray tube, CRT, those are the old monitors, old TVs. They used to be literally just firing electrons at a fluorescent screen. That's what you would see. And there's a couple other experiments. I really want to get to one that's really important, but what they discovered is, okay, we have electrons, we have protons, we have neutrons, so we have a bunch of matter, positive and negative. And so the question becomes, all right, how is an atom structured? Do I have positive bits of matter mixed together with these negative bits of electrons? Okay, because we've discovered the electron at this point. Or the electrons on the outside and the positive bits on the inside, right? And what's the magnitude of these things? Or does it look like a planet, right? Is the mass in the middle really large and the ring around the outside small? Or is it all condensed into one little space? And that's where the Rutherford experiment came in. So the Rutherford experiment, basically, he took a bunch of alpha particles. You don't need to know anything about alpha particles, but these are simply positive charges. So you have these particles that are just shooting forward in a positive manner. Okay, so you have these positive little particles that you're shooting through. And he's going to put him through a piece of gold foil. The beautiful thing about a piece of gold foil is you can bang it down and you make it really malleable, so you can make it super thin. In fact, you can make it so thin that it is literally like 4 atoms thick. That's how thick it is. And what he wanted to know is, okay, if my particles, which have mass, if these positive particles, if it looks like this plum pudding model where you kind of have a bunch of mass all kind of jumbled together, what we'd expect is none of this would get through. I would not see anything over here. Everything would come back in this direction, right? The gold foil would just completely block any of these positive particles coming through here. That's what the postulate, or if it's something else, we would have to know that. And so ultimately what Rutherford found out is most of them, most of the particles go straight through. So what this means is when I say most of the particles go straight through, what we discovered by this is that atoms are mostly, empty space. Okay, so they're mostly empty space, meaning there is nothing impeding the particles. Remember, these are alpha particles. Nothing is stopping these positive particles from going through. They're just going right through, and majority of them go through. And when I say majority of them, I mean that, because the second thing he discovered is 1 in 8,000. So only 1 in 8,000 was deflected. Okay, so 1 in 8,000 was deflected. And what that said is there is a condensed, or I should say, what that says is it didn't stop. They didn't disappear. Okay, so they didn't get absorbed by the nucleus or anything. But what we saw was the mass is positive. Okay, so the mass, whatever mass happens to be in the center, this thing right here is positive because it's pushing this down, right? Like charges repel, so it's repelling that beam downward. Okay, so 1 in 8,000 is deflected. And then finally, 1 in 20,000 comes directly back, appears in front of the gold. What this tells us is the mass is condensed in the center of the nucleus, or in the center of, well, in the center, that's it. And we call this a nucleus. Okay, so it is really condensed in the center. And that's what he discovered. The Rutherford's gold foil experiment was kind of groundbreaking. So most of the particles go through, saying most of the time they don't interact with anything. 1 in 8,000 are deflecting, saying something is deflecting it, meaning it's positive. And 1 in 20,000 rejects it, sends it right back at the. And he said that this was equivalent of taking an artillery shell, firing in a piece of tissue paper, and having that shell come directly back at you. That's how kind of amazing this was at the time. And so, and then finally, Chadwick discovered the neutron. So finally, we have this idea of what this looks like. So protons, and we have a nucleus which contains protons and neutrons. They're really condensed, and this is a bad representation almost because they're really condensed in the nucleus. And then we have these negatively charged electrons that are just cruising around the outside. They're traveling in what we call orbitals, or in spheres around the center of that atom. And so I'm going to leave you with this. So it's kind of hard to see from these pictures, but if I blew up this nucleus to the size of a golf ball, okay, so if I made the nucleus just the size of a golf ball, okay, how far do you have to travel in order to get to another nucleus? Okay, so if this nucleus was the size of a golf ball, you have to travel 2 miles before you run into another golf ball, which is another nucleus. So when I say that it is mostly empty space, that's what I mean, right? So there is literally miles of distance between those nuclei. Okay, again, the atomic world is small, but a nucleus composed of protons and neutrons is tiny in comparison to everything else. So keep that in mind. Okay, so this is the development of the atom. Really good work with discovering all of these different things without the technology to do it. But this is kind of hopefully the thing that you take into the next lecture portion, which we're going to define even better what an atom actually looks like.